If you know me, you know there are two things I love: structure and stormwater. And this building got a little bit of both. Alright, so above me, you can see these are new floor joists on this 100-year-old house. And some steel beams. And more steel beams. And more steel beams. Why? Let's start with the original house. This used to be the first floor. There was this wall here that provided structure, and this here that provided some structure. I gotta remember now. Honestly, don't remember which way the joist originally went, but I think no, they went this way and they set on this wall. And there was a big beam in the ceiling here, and so it all set here. But we opened it all up. So the first thing we had looked at was essentially putting a big beam from here to here that would have gone essentially right there, catching this steel sitting on the door. And that load, because you always have to think about how those loads get to the ground, it used to come down to a pier here, this thick rubble foundation, and a thick rubble foundation. This is, you know what, hold on. That was more than a foot thick of stone, plus the pier, and again, more than a foot thick of stone. And there was a beam that ran on top of that. And that beam used to carry the load of this wall, which used to carry, let's go upstairs, mainly this, and you can see it's disconnected here, but you can do the math and sort of figure out, okay, if I've got a load coming here and here, how much is actually having here, what size do I need, that's all doable. But the idea was that, this load came down on the wall, which came down on the beam, which went onto the piers and the exterior rubble down to the ground and set on a footing. And like I said, we got rid of all the walls in here and then rearranged them all here and changed the stair direction. The stairs used to come up and essentially catch that structural wall there and land there. Now we're going up this way. So we have to carry this opening, the whole open downstairs, frame it from side to side, and make it work. This is all an addition. This was easy to figure out. And honestly, we had done the math, and the first version of what we came up with, now this is where it gets interesting. This is something that becomes problematic for some architects. And structural engineers really seem to understand this well. Not all architects do, but some do. There's things that meet code, and then there are things that are comfortable. For this span, it's almost 28 feet from side to side. The code allows, and I'm gonna get my math wrong, I'm just gonna make up numbers at this point. The code allows about an inch of deflection. What is deflection? That means that when you start loading up that floor up there, it is allowed to dip an inch, and there is no structural issues. There's no concerns because the span is long, but that is uncomfortable. When you're walking up there, it feels like the floors are bouncing. So we had re-looked at it and tried to figure out, how do we do this and not lose ceiling height? Because down here we've got a pretty decent ceiling height. I'm gonna turn around. I can't reach, there's significantly more room above me. It's over 9 feet. And then upstairs, because this is eventually gonna be $1 million house, the ceiling heights were 8 feet. So we both bumped the height upstairs, but we couldn't go too tall because we had a height limit from zoning. So we had to find a way to both raise this, but not make these too deep. Because it could have been easy to just make these 16-inch deep beams, not have the deflection, use some engineered lumber and make it work. But we didn't want to change this height by more than 2 inches, so that when we raised upstairs 6 inches, we weren't, wasn't losing a lot. So what we did is essentially take steel, sort of strategically placed. This is the one that's the most useful. It runs at the front of the stairs, across the whole house. It has a steel beam that comes down, and it carries the stair, the floor, and then the beams run off of the steel beam to the front of the house. Then from the steel beam to the next steel beam. And this seems excessive here, but this one was already in, and that span was too much to make the 2x10s work to get to here, because the deflection was too high. But it worked reasonably well to go from here to here. And then we just had this small span right here. And we already had this because that's the old end of the house. Just got distracted by a phone call. Anyway, so now we've broken this span up. The allowable deflection ends up less because the span's not so long. I'll give you a brief primer on how that works. Essentially, there's a formula. Your length divided by a number gives you your allowable span. 360 is the code minimum for total deflection. There's a combination. There's a live load deflection and a dead load deflection. Dead load is sort of the stuff that stays, the floor, the wood floor, the sheathing, the things that don't really move. And then the live load is, me dancing, jumping around here, because I am live and can move from place to place. And like I said, over 28 feet, you divide that 28 feet in inches by the 360, and you're almost an inch. And if your floor is moving an inch, you feel it. Whereas now we've broken that span up by, I think this is like the largest one, which I think is this one, is like 12 feet. Now we're less than half an inch. We're 0.4 inches. That's allowed for this to dip and move. And then we even went higher from there. I think we used 480 or 600 so that these floors don't move, or they move. They're gonna move, everything moves, but you don't have it to the point where it's noticeable. You don't have a full inch that the floor is dipping while you have a live load on it. And the other thing is materials, right? So like, one of the reasons we use 360 is because 360 is kind of like the limit of sheetrock bending before it starts to break. And there's actually different parts of the code that tell you have to use different numbers based on what the material is. And they're more for the exterior of the building. So like stucco has a really high number you have to use because it's more brittle. It's like considered like a concrete, right? So like concrete doesn't do well when it moves. It can move, but not much. Versus a vinyl siding, which, that thing can flex. It's plastic. PVC is a plastic. It can move. Versus a stone. A stone has a certain amount. It can move, but the other side of that is you don't want it to move too much because then it'll fall. It'll come off, or a tile or something like that. So that is one of the reasons why we have so many breaks in this steel here. And try to line the wall. So we lined it up here with this one side of the stair, here with the other side of the stair, and then this one back here lines up with the end of the addition. And that's it. That's our structure here.